I'm Sala, and in this video we are going to end the case study on manipulated and controlled variable selection. In previous videos, we discussed steady-state analysis with both SVD and polyhedron geometry, analyzing setpoint tracking, total disturbance rejection, and partial disturbance rejection. In here we'll discuss the transient case, frequency response diagrams for setpoint tracking and total disturbance rejection, as follows. We had this linearized model around a given operating point, and these were G and H. In previous videos, we discussed just the properties of the DC gain of G and H. In here, we'll use the full frequency response, not just zero frequency. With this admissible manipulated variable increments, we'll choose the worst case minimum absolute value, this, and this, to build our diagonal input scaling matrix, and also with the maximum increments desired in setpoint changes, then the most stringent case will be the one with maximum absolute value increments, because transient analysis will use symmetrical SVD sphere geometry. Then in this case the worst case is 2.6 and 0.15, so that we'll build again a diagonal output scaling matrix for setpoint tracking tasks. So these are the scaling equations and the scaling matrices, and in previous videos we did the change of variable to scaled units just with the DC gain. In here we'll do it with the full G of S, the full frequency response of our systems. For total disturbance rejection, output scaling EY will not be relevant in the computations, but as we are mixing setpoint tracking and total disturbance rejection, we'll keep that scaling in both problems. Regarding disturbance rejection, we need to scale so that scale disturbances are in the unit circle in this case. So if these are the disturbance increments we are trying to counteract, then the worst case will be the increment with maximum absolute value. So with 0.8 and 0.65 we graphed the disturbance scaling, and again we did the scaling in previous videos with just the DC gain, but we'll now use the whole dynamics. So we are ready for the transient analysis by doing this scaling and posing our problem that in setpoint tracking, when input is in the unit sphere in the complex frequency response, output must have norm than 1 in the complex space, and when disturbances are in the unit sphere in the complex domain, residual error must be 0 with some feedforwards without saturating inputs. So how do we do it? Well, if we just plot the singular value plot as a function of frequency, and we compare with 0 decibels, 1 in logarithmic scale, then we'd get this singular value plot, which basically tells me that up to this frequency, 2.4 radians second, extreme input maneuvers produce output increments larger than 1, but from that frequency onwards there is one maneuver, or two of them, in which extreme values of input cannot produce output increments of modulus of amplitude greater than 1, so our specifications will not be fulfilled. So excess gain at low frequencies enables us to achieve some ideal closed-loop bandwidth of 2.4 radians per second. Of course, this is sort of an approximate idealistic situation, because actual closed-loop bandwidth will depend on signal-to-noise ratio, how much we need to filter, robustness considerations, so maybe we wish to keep things smooth to enhance tolerance to modeling errors, and a lot of additional stuff. But this preliminary analysis tells me that in an ideal situation with good sensors, fast actuators, and a good model, I may be able to achieve close to this 2.4 radian seconds bandwidth, which somehow is related to the rise time in my transient step response. So good. This would be a quick and dirty analysis of the capability of following setpoint changes in a fast enough way. We'll now analyze which is the maneuver that we cannot accomplish at this frequency. If we recall, when I get the frequency response at 0 radians per second, I got the DC gain matrix, and its singular value decomposition gave me the principal input and output directions and principal gains. So the difficult maneuver at DC was basically moving the second output. That was the harder stuff, but we had a 50% margin, so a steady state setpoint tracking was feasible. If I now compute things at 2.374 radians per second, I evaluate the frequency response. This is a complex matrix, so it's not too easy to understand, but that's when SVD comes to help. We have two real principal gains. This is one, because this is the frequency in which the minimum gain crosses 0 dBs, and then the output directions associated to each of the gains will tell me additional information about the maneuvers. For instance, the low gain maneuver is that one, and then in a general case, the modulus indicate amplitude of the input or output maneuver, and the argument indicates, well, the phase shift associated to that maneuver. In this case, the difficult maneuver is still in phase. There is no difference of argument of these two elements, so somehow it's the same maneuver as in DC, telling me that basically the most difficult stuff at that frequency is still moving output 2. So it's good because then it's easy to quickly explain what this means. This means that moving output 1 is easier than moving output 2 at DC gain, and so it is up to 2.4 radians per second. So we will be able to control the first output with faster closed loop dynamics than the second output. So this is the analysis of the reference tracking problem. If we now go to the total disturbance rejection problem, then this will be the feed-forward with the pseudo-inverse that would do the trick and totally cancel the effect of disturbances if they were measurable or observable or whatever. So this feed-forward has 3 outputs, which are controller actions, and 2 inputs, which are disturbances. And then in previous videos we just analyzed the DC gain. Now if we analyze the whole frequency response, then the singular value plot in frequency tells me that we can totally cancel the disturbance effect if disturbance movement is slow, up to this 16-17 radians per second, because all manipulated variables have amplitude less than 1 while being able to totally cancel the disturbances. That does not happen from this frequency onwards, in which a worst case disturbance cannot be totally cancelled. It seems that the decay of G at high frequency is faster than the decay of H, so disturbances win in high frequencies. If there is somehow a decay on H, even if I cannot totally cancel the effect, maybe the residual effect can be made low enough. That would be a partial disturbance rejection in the transient domain, but okay, things would start getting complicated then. If we reach such a precision in our conclusions, then what we should do is a full H infinity control problem. which is out of the scope of this analysis in this video. So this is the transient analysis regarding total disturbance rejection. As a last remark, we may consider this assumption that set points and disturbances are in the 4-dimensional unit sphere and check whether we are able to cancel both set point changes and disturbances in a worst case scenario inside this 4D sphere. Okay, this is not reference size 1 and disturbances size 1, because in that case that would sum up to 2. So we have sort of square 2 conservative some stuff in size. But with that in mind, in order to do this, we just need to consider reference as a particular kind of disturbance in which h is equal to -1. Because in this case, this thing that we call loop error would be the residual error when subject to that disturbance. So combined disturbance rejection will amount to finding a control U that makes this error equal to 0 and checking whether it saturates or not. Then the needed control action would have this formula, pseudo inverse time this thing changing sign. So that is exactly what I am computing here in this line. This pseudo inverse will be the thing I would need if h was 0, just set point tracking tasks. And if I have both D and R, then I need this real 2 feed-forward matrix. Note that it has 4 inputs, 2 disturbances and 2 set points, and 3 outputs, 3 control actions, so sizes are okay. So if I draw the singular value frequency plot, sigma, then as my output now is in input units, the input must be lower than 1, so this will be the closed loop bandwidth in which combined set point plus disturbance rejection tasks will be feasible without actuator saturation. In order to compare, we will superimpose the combined set point and disturbance control demand with the only set point pseudo inverse of G and only disturbances, the FF feedforward 1 we computed earlier on in this video. Then in blue we have the combined set point and disturbance worst case effect. In yellow we have the input requirements for just set point tracking. They are easier, of course, so the yellow principal gains are below the blue lines. Recall that the units of these transfer functions we are comparing, the outputs of them are manipulated variables U, so an easier problem is the one with lowest required manipulated variable increment. So well, yellow is easier than blue, and of course red only disturbance rejection is easier than combined disturbance rejection plus set point tracking, of course. So this is the final comparative analysis, and as we can see basically in here, the difference between set point tracking and set point plus disturbance is negligible. So it seems that the difficult thing limiting my closed loop control bandwidth is that I require too high a set point. Indeed, if I require just disturbance rejection, my bandwidth will be much higher. So this is it. We conclude the video here with this transient case, and this concludes also the case study. And as I said, this is sort of a preliminary approach because the whole transient analysis with maybe different error set point and manipulated input amplitudes in different frequencies, then okay, that general problem is the basic problem statement of H infinity control, whose in-depth analysis is carried out in other videos of this collection. So we end up here. Thanks for watching.